Hello, this is Scott Harler from the Office of Space and Defense Power Systems. So we're back at it again for another issue of the NEUP briefing. So in my group, we do a lot of really interesting things. We develop space and power defense power systems for both NASA and national security users. And the benefits are that we enable customer missions in locations and environments where you can't use, solar power or batteries. So our key research and development areas are to develop materials that can withstand working in harsh environments. Also we need something that is reliable, because once you send something off into space, you don't get it back. You have to make sure it works. So as I said, we provide nuclear power sources for space science and exploration missions and national security applications for which solar and other power sources are not feasible. And we maintain the capability to produce plutonium-238 through our work at Los Alamos National Laboratory. We report to the Deputy Assistant Secretary for Nuclear Reactor Technologies within the Office of Nuclear Energy, so that's NE7, Dr. Kelly. And we work with NASA to provide radioisotope power systems for use in space. Okay, we maintain our laboratories. We have support from Oak Ridge National Laboratory, Idaho National Laboratory, Los Alamos. So I put this slide up last year. It shows all the missions that have had radioisotope power systems on them before. So this year we had a major victory in going to Pluto. So when my daughter was in 4th grade, I was making the presentation about going to Pluto, and I told her class that it would arrive in 2015, and they all just kind of said, oh, wow. But we did it, and this is how we now see Pluto. It's no longer just this little pixelated picture. This is a real life color photo of Pluto as a result of the mission that we supported back so many years ago. We also have ongoing the Mars Science Laboratory. This is the little Curiosity rover that you've seen probably. If you're a science geek at all, you've probably seen the Mars Curiosity rover. We're going to have a redo of this in 2020. It's called the Mars 2020 rover, and it's going to be built pretty much the same with just a different science payload on it. And it will be using the same multi-mission radioisotope thermoelectric generator. So we also have a small project working on nuclear thermal propulsion for NASA. That's another area where we support NASA. The key components of our power system is how it's designed for safety. These things have to survive all kinds of postulated accidents, both at the launch pad, re-entry accidents. We design safety from the inside out and outside in, as our safety guy likes to say. It's not the most efficient way to make electricity. These things, we're lucky if we're 6 or 7% efficient, but that's just the nature of the business. We use a lot of heat from the decay of plutonium-238 and only use 6 or 7% of it at the end of the day to make electricity. So our challenges are always to enhance the safety performance of these systems. We always want to plan for the next accident. We want to make sure that we're not letting any of the plutonium-238 escape out into the atmosphere or into the environment in any way. And we're also trying to improve performance of the systems, because it costs a lot of money to fly systems. I don't remember what the number is exactly, but dollars per kilogram to go on a NASA mission are very expensive. So we try to get our weights down as much as possible. And as far as our manufacturing processes, we do what we can to keep our radiation worker doses down. We use shielded glove boxes. We try to ensure that we don't have to do rework by making high quality items the first time around, so we don't have to rework them. And then we also try to reduce the amount of waste that we generate, so there's a smaller footprint at the end of the day. So last year, I wanted to thank you all for your proposals that came in. I felt like those were really high quality proposals, and we did select one for the MRC 241 safety studies. So thank you for that. But this year, we want to start working on some conceptual designs for some small reactor systems that can be used for both NASA or national security. And our thinking is that eventually we are going to be getting to Mars. We may stop at the moon first, but we want to get a reactor system that's going to be reliable, that can be rated to support human interactions on a foreign planet or on the moon. And we're hoping that we'll get some innovative design concepts with this year's solicitations. Our hope is that we don't have to go into exotic materials manufacturing, especially on the fuel forms. There's been a lot of information developed over the years on different reactor fuels that could work just fine for a space mission. So we would suggest don't go with something exotic. Stay with something that we know. And then we're also looking for proposals for the development of advanced neutronic and reactor physics fuel models. You know, we need better computer modeling for these smaller reactor systems. We're not building a huge Westinghouse, you know, baseload plant here. We're doing something smaller. So we need a better computer code that is more matched for these smaller reactor systems. Our thought is that NASA will probably be coming to us for a 20,000 to 30,000 pound thrust nuclear thermal propulsion rocket sometime in the near future. And DOE would like to stick with NERVA fuels for that activity, because we've got a huge database of information from NERVA. We spent, I don't know, billions of dollars in the mid-60s through, I guess, the early 1970s. And then finally, we would like a small terrestrial reactor system. This would be for, you know, in the area of 100 kilowatts to 1 megawatt of electric output. And it's for perhaps forward deployed military bases. Can't say for sure, but that's the market that we're looking to support. And then it would be self-contained and easy to both emplace it and retrieve it at the end of life. And it has to be of a size that can be easily transported on 1 or 2 truckloads. So that's about where I am. If you have any questions, please let me know.
First question, Scott, is improving plutonium-238 production considered in this work scope?
I think we have a pretty good handle on PU-238 production, but I would be willing to look at any proposal that you would have on 238. Yes.
What structural materials might be of interest for these small reactors?
All right, so structural materials. Stainless steel is something that we really like. It has good radiation resistance properties. We like UO2 as a fuel form. It's been in fast reactors before. We think it's fairly well characterized. One of the designs that we were working on back in the mid-2000s was a NAC-cooled fast reactor. It used reflector drums. So that seemed like it was a workable solution for a small reactor system as well. That's beryllium oxide.
Is radiation damage an issue to be considered?
We find that if we stick with some of the existing fuel forms, that the total displacements per atom are really not that high. So I guess from a standpoint of electronics, yes, radiation damage would be important. But from a fuel form, I don't think that's going to be an issue.
Is there any specific power density level that you are expecting?
I don't have a number in my mind on that. So how do I get back to folks with a more specific answer, since that one wasn't?
For more specific answers, we will post all of these questions, and Scott will have you write out a more detailed answer once you get back to your desk and have a little bit more information in front of you.
Sounds good.
And we'll post all of those in a webinar specific question and answer that participants can use in prepping their applications.
Okay.
Is developing advanced thermoelectric generators within the scope?
We're always looking for new technologies in the thermal electrics, so yes.
Is proliferation resistance a potential issue?
Proliferation resistance is always an issue, especially when you're talking about HEU. My personal feeling is that most of these systems are going to be on a government-controlled site, and there's going to be plenty of guards that are employed to keep that material safe from any kind of external threat.
Can the emphasis of the proposal be on the thermoelectric material itself, or does it require the reactor design?
The reactor doesn't necessarily have to be coupling to a thermoelectric system. It could be coupling to a Brayton, it could be coupling to a Stirling. So I don't know how to answer that. We feel like we can get higher efficiencies, but there's downsides to it as well because you have more moving parts. So you have to balance all of those things.
Is the call this year mainly focused on conceptual design, or do you also support experiments and prototype building?
Primarily paper studies at this time, conceptual design.